Thank you for the introduction. And well, first of all, thank you for inviting me to speak in this nice event. It's really a pity that we can't all be there and interact in person, because I was looking forward to meeting some of you and maybe finding some relations between my work and some of the nice talks I've seen. But okay, at least I will try to give you an idea of some aspects of my work. So I will be introducing this topological recursion, and in particular, its relation to cohomological field theories and to some discrete surfaces. So yeah, at the beginning, I will introduce these general topics. Then I will focus for a while on this joint work with Raphaël Belliard, Séverin Charbonnier, and Bertrand Eynard on the Witten spin class. And then I will briefly mention some ongoing and future work. So let's start by this topological recursion. So the topological recursion was introduced around 2004, sorry, by Chekhov and Eynard in the context of large size expansions of matrix integrals. And then later, around 2007, it was upgraded to a universal theory beyond matrix models. So you don't really need any matrix model to run it. And well, I will just try to give you the idea. There are way too many details in these slides, but I will try to help you focus on just getting the ideas. And then if someone is interested in some of the details, we can discuss more. So our general goal is to count, in some sense, surfaces SGN of genus G with n boundaries. That is, I say also that surfaces of topology Gn. And by counting, I just mean something that needs to be made precise in every particular case, because this topological recursion applies to many different contexts. But in general, we want to somehow count surfaces. And we do this by using this topological recursion that associates to some initial data that we call spectral curve, a family of differential forms omega Gn. So it's a family with two indices, G and N. And we do this by recursion on this quantity 2G minus 2 plus N, which gives us some kind of notion of complexity of the surfaces SGN. So we start by the topologies of disks and cylinders, and then we produce all the rest of the topologies. So the omega Gns will tell us something about our surfaces SGN. And these omega Gns are differential forms on the Riemann surface that is part of the initial data of what we call the spectral curve. And it's realized as a ramified cover of the sphere by this map X. And it also consists of another map Y, another meromorphic map Y on the surface. And then with Y and X, we build omega 01, which has to do with the topology of the disks. We also have the data of the topology of the cylinder, so a B differential, omega 02. And with this, we build the rest of the topologies. Then I give here some details of the initial data, but I will skip this and just give you a brief idea of how this procedure of topological recursion works. So here I gave a graphical representation. And so don't be too overwhelmed by this picture. It's just to give an idea of how the formula works. So here we represent omega Gn by just this surface of genus G with n marked points in this case. And we build the information for this topology as a sum of ramified points of X. So remember, X is very important in the initial data, and we take a sum over ramification points. And for the classical topological recursion, these ramification points have to be simple. So we only have two sheets of the cover coming together. Okay, this is what I want you to remember. And then we take residue calculations on these ramification points of some quantities that we build with simpler topologies. What do I mean by this? Well, you can actually see that the terms of this sum are in correspondence with the ways of cutting a pair of pens. So by pair of pens, I just mean a sphere with three boundaries, so something of topology 0, 3. From our surface SGN. So these trivalent vertices represent this pair of pens. And then we need some quantity which is the kernel of the recursion. I don't give any details. And if you cut the pair of pens out of SGN, well, here you have all the possibilities that you can obtain. Either you obtain something connected or you obtain something disconnected, and here I sum over all possibilities of getting something disconnected. Well, one of the nicest features of topological recursion is that it's universal. So the same formula will work in many different contexts. And here I give you some examples. This list is way too long as well, but let me comment just a bit on them. I just gave this long list because I thought, okay, maybe this is instances that would interest some people in the audience. So this topological recursion is also nice because the omega GNs have interesting and powerful properties. So for example, they are symmetric, even if Z1 seems to play a special role. They are actually symmetric in the Z1, Zn variables. They have poles at ramification points. They have controlled deformations along families of spectral curves. Well, some properties that I don't give the details about. Let me just mention some contexts in which we have topological recursion. So for example, if you take this specific spectral curve, the Lambert curve, topological recursion counts for you the number of coverings of the sphere, of ramified coverings of the sphere, and this is given by Hurwitz numbers. If you take this other spectral curve, topological recursion reproduces Mirzakhani's recursion for Weil-Peterson volumes, which are just volumes of the moduli space of hyperbolic surfaces. Then it also has to do with mirror symmetry, with Chern-Simons theory, with statistical physics models, with integrability, WKB expansions, conjecturally with knot invariance, just to give some instances. And here you have all the papers that you can click if you want. And nowadays it's an active topic of research also to extend the topological recursion to the non-perturbative world, making use of this resurgence theory that was nicely introduced in the talk of Gerald June. Okay, but in this talk I will focus on the relation to cohomological field theories, and about that I will give a bit more details. So let me start with the definition of moduli space of curves. So MGN is just complex curves of genus G with n marked points up to isomorphism. Then one needs to add some structure to this set, and it actually has a very nice structure. And this moduli space is not compact, but we can compactify it in a very classical way using the linear-Mumford compactification. In this case, we just add nodal curves. So instead of considering just smooth curves, we also consider this type of singularities, like in here. And well, in the moduli space, every point represents a surface with n marked points. And then above this point in the moduli space, we find the actual curve. And we can take the cotangent line to the marked point I. And if we move this marked point I along the families on the base, we actually find a bundle that we call Li. And we have n of these bundles because we have n different marked points. Then if we take the first term class of these line bundles, don't worry if you don't know what this is just a cohomological class associated to the line bundle that tells us some information about the bundle. If we take the first term class, this is what we call the psi-classes. And the psi-classes are very important. They are the building blocks of the cohomology of MGN. And the study of the cohomology of MGN is a very active field of research. And actually it's very complicated, and we study mostly a subring that is the one that contains, it's believed to contain all the geometric information, which is called the tautological ring, and in which we have relations among these very nice natural classes coming from geometry that we call the tautological relations. Okay, and we can also compute the intersection numbers, which are just integrals over the moduli space of these cohomology classes that give us information, geometric information about this moduli space, about this cohomology. And well, these numbers are 0 unless the sum of the degrees is equal to the dimension, as you can imagine. And well, it was a very important problem to compute these numbers in algebraic geometry, but it was very, very complicated to compute them. using just algebraic geometry. The people were able to compute some of them for low topologies and low Ds, but it was really difficult to imagine that we could compute all of them. And then Witten in the 90 came with his amazing conjecture. He said, well, actually, if we build the generating series of intersection numbers, this will satisfy the Korteweg-de Vries hierarchy, the KdV hierarchy, which is just an infinite set of PDEs that are compatible. And this KdV hierarchy starts with the KdV equation, which is just this one over here. And the series, the generating series of intersection numbers, has to satisfy the Korteweg-de Vries hierarchy and also the string equation over here. And these two features uniquely determine F. Well, this was something amazing for mathematicians because this allows you to compute recursively all these intersection numbers that were so complicated to compute just with geometry. And from the physical point of view, this was natural for Witten to conjecture, because his motivation was just that two different models of 2D quantum gravity should coincide, which is something quite surprising for a mathematician, but I guess kind of natural for a physicist, well, especially for Witten, I guess. So yeah, and in one sense, you can either discretize, so you have to regularize an integral which is ill-defined. The audience knows a lot about. And you can either first take conformal classes, and then you will get the intersection numbers, or you can discretize the surfaces, and then this has to do with a problem that can be solved and that is related to the KdV hierarchy. This was his motivation. And well, in the next slide, I just give you the explicit, an equivalent way of stating Witten's conjecture, in which I give all the details. So in case you want to start computing intersection numbers, you can do it with this slide, but I will not give many details. So these are the Virasoro constraints. They are just linear differential operators, and they annihilate the partition function. And this is equivalent to Witten's conjecture. So, okay, just to summarize, in 90, Witten formulated his conjecture that intersection numbers satisfy the KdV hierarchy. Then Kontsevich, just 1 year later, was able to relate some discrete surfaces, some combinatorial maps, we will call them in this talk, to a matrix model. Then this matrix model can be related to the integrable hierarchy. And on the other side, the combinatorial maps can be related to the intersection numbers. And like this, Kontsevich could produce a proof of Witten's conjecture. So nowadays, if we place topological recursion in the middle, that appeared later, we understand very well the relations to this problem and all the features around topological recursion. So this is a very, very nice problem in which we understand all these nice features. And yeah, just to tell you a bit more details, topological recursion applied to what we call the Airy curve, which is just, it just looks like this: x is equal to z squared over 2 and y is equal to z. It produces for you these intersection numbers in a recursive way that is actually equivalent to Witten-Kontsevich result. And well, this feature of topological recursion, counting these intersection numbers, can actually be generalized in a successful way to many cohomological field theories. So by cohomological field theory, I just mean like a version of topological field theory, but actually kind of an extension of topological field theories, in which we take values in the cohomology of the parameter space, which is the moduli space of curves. So we take V, a vector space with a non-degenerate symmetric bilinear form, eta. Then a cohomological field theory is just a collection of morphisms like this that satisfy some axioms. So these morphisms have to behave well with respect to degenerating the surfaces. And this is what the axioms tell us. I don't want to give the details, but yes. We can also define the correlators of these cohomological field theories. And they are defined just like this. They are the integral over the classes given by these morphisms, the cohomology classes. They have to be evaluated at these vectors that belong to the vector space. and then multiplied by the psi-classes. Remember that the psi-classes are like the building blocks of the cohomological field theories. So we define in general the correlators of the cohomological field theory like this. And well, I forgot to say that we abbreviate very often cohomological field theory as CoFT. And here I just gave two examples very briefly. So if we take a vector space of dimension 1 over Q, the trivial cohomological field theory is if we just take all these morphisms to be 1, then we obtain the correlators are just Witten-Kontsevich intersection numbers. So okay, it's a trivial CoFT, but the intersection numbers are not trivial at all. And another possibility is to take this cohomological field theory even with this kappa class. Well, this doesn't really matter, but like this, you can get Weil-Peterson volumes that are related to this hyperbolic geometry that I was mentioning before. So, okay, this cohomological field theory defines for us a product, a quantum product on the vector space. And it's actually commutative and associative by the axioms of the cohomological field theory. And like this, if the cohomological field theory also has a flat unit, so it has to have a special element, we say it's semi-simple if this vector space forms with this product forms a semi-simple algebra. These semi-simple cohomological field theories are much nicer to study because they actually have the huge Giventhal group, which is a very important group that acts on semi-simple cohomological field theories. And using this action, we actually, Telemann found this classification of semi-simple cohomological field theories. So given any cohomological field theory, it can be determined just by the degree 0 part. So the associated topological field theory, we say. And just something called the R matrix, which is something very useful to classify these these cohomological field theories because it helps you to compute everything you want. Yeah, there are some problems, and first, there are some examples which are non-semi-simple, like the one that I will talk about in this talk. It's Witten's R-spin cohomological field theory. In this case, the vector space is of dimension R-1. And what I just want you to remember is that, this is a cohomological class that was constructed by Witten for genus 0. And he gave some hints of how to do for higher genus, but it took many, many years to algebraic geometers to actually construct properly, rigorously, this cohomological class. And still nowadays is considered very difficult. So the construction is very complicated for higher genus. And well, it's of a pure cohomological degree given by this quantity over here. These are the primary fields, which are just numbers between 0 and R-2. This is what you just need to remember for this talk. So, okay, here I summarize the situation for the Witten-Kontsevich case. And as I promised, this setting for the Witten-Kontsevich case generalizes very nicely for semi-simple cohomological field theories. What do I mean by this? I actually mean that there is a correspondence between topological recursion for spectral curves just with simple ramification points and semi-simple cohomological field theories. So given any topological recursion, we can construct the corresponding cohomological field theory and the other way around. But so this result is really, really important. It was very fruitful to start to establish many relations between many worlds that have to do with topological recursion and algebraic geometry. Unfortunately, we have no idea really how to reach non-semi-simple cohomological field theory. But in this talk, I will tell you about this particular instance of R-Witten class, in which we know how to relate it to the topological recursion and to all this picture over here. And in that case, it's not semi-simple, so it's one step farther. And this class of Witten is especially important for the study of this tautological ring of the cohomology ring of MGN. So okay, in '93, Witten gave his more general conjecture with respect to the one that I presented before, in which he said that the intersection numbers in which we add here Witten's R-spin class actually also satisfy a hierarchy, but this time is RKDB hierarchy. So for R equal to 2, this result was proved by Kontsevich, as I said, and it received many proofs afterwards by Mirzakhani, Okunkov Pandaripande. And well, nowadays we have really many proofs. And as I said, we understand quite well all the relations for this R equal to 2 problem. But for R bigger than 2, this only received a proof in 2010 by Fabershad and Zonkin. And as I said, the class is still considered very complicated. And the proof, well, it's super nice that they were able to prove this result, but it doesn't give a lot of information about this class. So what we wondered is, can we complete this picture that we understand very well for the R equal to 2 case in the general R case, since this class is so fundamental for these tautological relations that, as I was mentioning. In particular, can we make the connection to the combinatorial side? This is what I will present a bit in this part of the talk. So I start by telling you that in this part of the talk, I will talk about some generalized Kontsevich graphs that I will also call maps. So what do I mean by map? By map, I mean here a combinatorial map. It's just an embedding of a graph into an oriented surface of genus G. We say that the map is of genus G in that case. In such a way that the complement of the graph in the surface is homeomorphic to a disjoint union of disks that we call the faces of the map. And then we say that the map has n marked faces or boundaries if some of the faces of this map are marked in some way. So let me give some examples, and we consider this concept up to isomorphism. So in here, for example, we have a map of topology 1, 2, because it's a graph embedded on a surface of genus 1 and with 2 boundaries, because it has these 2 special faces that are marked here with an arrow in such a way that the special face is sitting on the left of the arrow. So it's a map of genus 1 with 2 boundaries. In here, we have 2 embedded graphs on surfaces, but they are not maps because the gray surface, the gray faces are not, don't have the topology of the disk. So they are not okay, but we can add some edges and then they are perfectly fine maps. So this is just to give an idea in general what we mean by map. Now I will introduce the generalized Kontsevich graphs that I will also call ciliated Kontsevich maps. So these graphs, for this work, we actually need, it's a quite a technical thing, but we actually need 4 sets of these graphs that I will introduce in with increasing difficulty. So they all have degrees, so they all have black vertices, and with the restriction that the degrees of these black vertices are between 3 and r+1. And then in the first set, we just have these black vertices, and we have 2 types of faces. We have the faces decorated with lambdas, that are the decorations for internal faces, and the faces decorated with Z1, Zn, that are the decorations for the marked faces, so for the boundaries. So remember, just internal faces and boundaries. Then in WGN, which is actually the most fundamental for our work, we just introduced this cilia. By cilia, I just mean this white vertex in the middle of the marked faces. And they are just of degree 1 in this for this set over here. And well, that's why I call them the cilia of the map. Okay, so these are the uniciliated maps. And here the only difference is that we also consider this square vertex instead of the black vertex. The only difference is that here we don't have this restriction on the degree. So this is important for some technicalities. But don't worry too much about that. And in this case, we have multiciliated, in which we can have a higher degree for the white vertices. And these white vertices have to satisfy this star constraint. By this, I just mean that the faces around the white vertex have to be different. So in here, for example, we have this face and this face that are the same. So this doesn't satisfy the star constraint. It's okay. It's a technical condition on the white vertices. And then we want to enumerate in some way. We want to organize these graphs on families and compute their generating series. And for this, we need to introduce the degree, which is just r+1 times the number of edges minus the number of vertices. So if we fix the topology, so remember that for these sets, I didn't say it, but we were fixing all the time the topology in these sets. So here, if we fix both the topology and the degree, these sets are all finite. So then we can introduce the generating series. And for that, we need first to introduce some weights. They look a bit complicated and a bit out of the blue. I will give in the end of the talk briefly a motivation why we gave these type of weights and why they are like the ones that solve the problem that we want related to these intersection numbers. So we need the potential of the model, which is just a polynomial of degree r+1 with these parameters v. And then if we decorate an edge with the decorations given for the faces around this edge by A1 and A2, we give this weight for the edge, that is just the propagator. Then if we decorate the faces around the vertex with these AIs as well, we give these weights for the vertices, for the black vertices. Observe that they use this potential over here. So they really look quite complicated, these weights. And then for the white vertex, at least, we give this very simple weight, which is 1. Then with all these weights, for every map, G, we multiply all the possible weights. This is the weights that we give for the square vertices, but okay. We get the weight of the map. And with this, we can define the generating series of our maps. So for example, for unciliated maps of topology Gn, so it's the set F, we just sum over all possible graphs of weight. So we sum over all possible graphs these weights associated to the graph over the number of automorphisms. And then we also introduce a weight that keeps track of the degree of these maps. And these are formal power series in the variable alpha to the -1. But once we fix the power of this formal parameter, it's a polynomial in the rest of the parameters, okay? Then we do the same for the other sets. And here, just to give you an example and an idea of how this works, and this will become important in the end of the talk. This is an example of topology 1,1, and it's for the case without internal phases. So we only have one phase that is given by the boundary, and we have genus 1. So we just have that 2g minus 2 plus n is equal to 1. So the degree is r+1. And then with an easy Euler characteristic count, we can actually see that if we want just one boundary, this means that for ciliated, this will give us just one white vertex. And this, with this Euler characteristic count, we can actually see that the only possibilities for the black vertices are the possibilities that I draw here. So we only have these 4 graphs. So we can have either 3 black vertices of degree 3, and then we give these 3 weights of degree 3 for the vertices, and these 5 weights for every edge. So we have these 5 propagators. Then for the possibility of 1 vertex of degree 4 and 1 vertex of degree 3, we have these 2 types of maps. So that's why we get a 2 in here. And then we also have the possibility of a vertex, a black vertex of degree 5. And for that, we have just this weight over here, this vertex of degree 5 and these 3 propagators. So we can compute with this formula over here that is, okay, it takes some work to prove, but you can believe me. And this is the contribution for this generating series in this special case without internal phases. This will become maybe important in the end of the talk. So in this slide, this looks quite scary, but I just want you to remember that we are able, with quite a lot of work using combinatorial decompositions of maps, we can relate all these generating series. We can relate the unciliated maps to the uniciliated maps, then the uniciliated to the multiciliated, and the square ciliated to the uniciliated. Okay, so we can find relations among the generating series using some heavy combinatorics that I will not give the details about. And then what I want to explain a bit is the idea of how we get the recursion. So how we are able to solve this problem. So for the moment, I'm just solving the problem. And in the end of the talk, I will just briefly give you the motivation of why we introduce these complicated weights. So for this, we find kind of stat recursion, because it's just a generalization. In this case, it's quite much more technical than the original stat recursion, but okay, he was the first to give this type of recursion. So in this case, we need to define, so for this, to find the good recursion, we need to define these 4 sets of maps, as I said. And well, in the end, with the right sets of maps, we are able to find the recursion that we want. So let me give the idea of how this stat recursion works. So for this, we just, our idea is we will just take any square ciliated map, and we erase the first cilium. By cilium, I just mean this edge that goes to the white vertex. And then we introduce a ambivalent vertex on the following edge around the square vertex in the clockwise direction. Okay, and then doing this, we actually find 4 different possibilities that I will give you the idea about. So in this case, the following edge is just adjacent to a face that is internal, that is decorated with lambda j. In this case, it's very easy. We just remove this edge. And since we have removed this, we actually need to also add here the propagator to compensate this, because we want to have this equality, right? And here we introduce this edge. And since we introduce this, we have to remove this propagator. And this will have to do with the weight associated to the square vertex. Okay, and then once we have this equality, we can use one of the previous relations that I gave you. We just use that the multiciliated are related to the uniciliated. Okay, just believe me. And then the contribution for this type of situation is just given by something like this. Okay, this all looks complicated, but I hope you are getting the idea. The next possibility is that the following edge is actually adjacent to a face that is decorated with Z. So it's a boundary, not an internal face. Sorry for this bad noise. I hope it's not, it doesn't last too long. So in this case, we first are able to remove the cilium with one of the relations that I gave in the previous slides. And then it's very similar to the previous case. We just use the same relation as before, and we get a contribution that looks like this. Then another possibility is the possibility in which the following edge is adjacent to the first marked face. So we have the same face in here. Then we can make this transformation, and we can cut in here. And then this factorizes in these 2 types of graphs. So we have this contribution, this sum over all these products of graphs. And the last possibility, okay, sorry for that, is actually the same, but we have a genus connecting these 2 components. So when we cut, we don't have something disconnected, but we have this type of maps that give this contribution. Okay, so what we did is just, we took all possible maps that contribute to this generating series U, and we established bijections by making this bijective procedure of removing the first cilia and adding it in the next phase. And with this, we found this recursion over here. This recursion relation is in 2g plus n plus delta. But what we actually want is a topological recursion. So we don't want a recursion also on the degree, because then this recursion is difficult to handle. We just want to get rid of this part. And well, here I didn't give the formula for 0,1, but believe me that it's simpler than this. So we want to simplify this complicated recursion and actually transform it in the universal recursion given by topological recursion. Okay, so for we take this formula for 0,1. We call this x v prime. We call y this quantity over here. And this formula for 0,1 gives us a relation between x and y that gives us what we call the spectral curve. And actually this y looks very complicated, but we can actually prove, this is what this theorem over here tells us, that there is a reparametrization of, so there is another parameter zeta, which is actually better, in which we can get an explicit formula for y. And what this theorem tells us is that there is a way to compute explicitly this new parameter and this y in terms of this new parameter. So, okay, just let me briefly sketch the idea on how to get the topological recursion from the touch recursion. So we had gotten a recursion for U and W a la tat. Then this recursion for the base topology 0, 1 and 0, 2 give us our initial data of the spectral curve of the topological recursion, which is called the spectral curve. And it looks like this. Then with this recursion for higher topologies, we are able to give a combinatorial interpretation of certain universal expressions. I'm not giving any details of these universal expressions, but they have to do with these loop equations for any matrix model, or some Schwinger-Dyson equations more generally. We also need to study the analytic properties of the WGNs. Oh, I'm really sorry for that. Then with 3, we are able to obtain the abstract, so the general shape of these loop equations that tell us that some combinations are analytic functions. And with all this technical work, we actually get the topological recursion that we wanted for the WGNs. But actually, we got this topological recursion for generic parameters. But for the intersection numbers, we are interested in a very specific case of the parameters. And for that, we need to actually take this type of spectral curve and send this epsilon to 0. And what we are doing is we are collapsing some simple ramification points into some higher order ramification points. And we actually need a more complicated topological recursion than the one that I briefly presented at the beginning. But okay, we can actually check all the details that what we want is true, that the limits work properly. And just to summarize what we did, we have the result of Faber-Shad and Dronkin, as I mentioned before. We were able to prove that the generalized Kontsevich maps satisfy the higher topological recursion. We related them to a matrix model. Then we were able to relate this matrix model to the integrable hierarchy. And then making use of this result, we are able to close the loop in here. So we are able to make the connection to topological recursion with intersection numbers and with intersection numbers and the combinatorial objects. So yeah, and in the next slides, I just give some details of this picture over here. Let me just point you to the most important features. So in this slide, it's the slide in which you see why we took these very complicated weights for the maps. So our generalized Kontsevich graphs, just generalize the Kontsevich graphs that he introduced in his proof of Witten's conjecture. He just considered this matrix integral, which is an integral over Hermitian matrices. And it's with an external field given by lambda. A natural generalization is this one that we consider here with this potential. And it's the one that motivated us to give this. So with some transformation, you can see that these complicated weights that I was mentioning appear in here. So this gave us the motivation that these were the weights that we needed to consider for our maps to work, to give the relation that we wanted. So we can find the relation between these matrix models and these unciliated, so these generalized Kontsevich graphs. And in the case of the ciliated, we need to take these correlators, which are given just by the diagonal elements of the matrix. Okay, and so just then this has some nice features with respect to properties of the topological recursion that I don't give the details about. And this is just, this slide just gives some more details of the picture that I gave before. So let me just summarize. We have our R-spin intersection numbers that are complicated to compute. The partition function of the generalized Kontsevich model provides the only solution of the RKDV hierarchy that also satisfies the string equation. Then this partition function is related to intersection numbers by the result of Faber-Shad and Dronkin. And using our relation of the graphs with the matrix model and then 1 and 2, we are able to relate our combinatorial objects to the intersection numbers. And these type of relations are quite important. They are usually called ELSB type formulas because they give us information of complicated algebraic geometry from using some elementary techniques of graphs. And in here, I just complete the example that I started before. So remember that we had computed this for topology 1.1. So if we take the specific potential that we need for the intersection numbers, we just get these calculations over here. And making use of our ELSB type formula, we are able to compute the intersection number that we want. And then I will just take 1 minute to wrap it up. Just say some brief words of what we have done so far. So here I just summarized the picture of what I explained. So in the talk, in this talk, I just talked about all these green arrows over here, but this work is also related to some combinatorics and free probability and symplectic invariance in case someone is interested in that. And we are doing some ongoing work on trying to understand more deeply this diagram that I gave. So with this work, we use the power of topological recursion to make directly this connection over here, which will help us find a new proof of this Faber-Savin-Zolkin result, and hopefully to understand better this Witten's R-spin class. So thank you for your attention.
Thank you very much.
Sorry for the noise and going over time.
Not your fault. All right. So now I should invite Riemann to comment.
Yes, so I should probably stop sharing.
So, does it work? Okay. So I will also try to share the screen if it works. All right. You see something?
Yes.
Yes.
All right. So that's my attempt. Okay. So, okay, first, thanks a lot, Elba, for the beautiful presentation and congratulations on the result. Okay, I don't think I can say it better, but okay. So the idea is, so all this is about extremely active research area, topological recursion, TR in short. And you should think of TR as part of or central part of a very large picture. And this picture is about really amazing connections between mathematical fields. Okay, there's a huge literature, and I really recommend to read at least the introduction of the article Elba was referring to. Well, okay, experts can read everything. So, okay, here's the picture. So this is taken from the labeling is taken from the article. It's a little bit different arranged. So anyway, so there is a deep relation between four large areas. Area A is enumerative geometry in matrix models. B is complex geometry and topological recursion. And then we have C, intersection numbers on the moduli space of stable complex curves. And D, integrable hierarchies. So, and Elba filled in her talk this picture with life in a very large family of examples. So some historical words, this was already given in the lecture. So the first example of such connection was between matrix models and KDB. This appeared in '86. There were 3 different papers which discovered this. And then Witten came up with this famous conjecture that this KDB hierarchy is related to intersection numbers. So as you heard, this was proved by Kontsevich, and the method was to produce from the intersection numbers a formulation of a very new matrix model, different from the Hermitian 1 matrix model. That's a deep step. And from that, he was able to get D, so integrable hierarchies. The middle topological recursion appeared later, I would say, after people had a lot of experience with many more examples. So in particular, the Hermitian two-matrix model was very important. And okay, it took some time. And in 2007, it was more or less completed by Eynard and Orantin as a universal framework. So I show you back the slide. So here, this is the centerpiece, which we appreciate. Good. Yeah, you have heard this in the talk. So you organize some initial data into a spectral curve. I will not read it again. And then from this initial data, you build recursively in the negative Euler characteristic family of Mirimov differentials on some Riemann surface. And then you have to read it properly. After suitable Merrill transform, you get the intersection numbers of kappa psi-classes, so directly from the omega gn. So many examples are known today. Elba gave few of them, and well, shared it more. All right. So what's the result? Okay, you have seen there is these four areas which are connected, and for me it's easiest to explain it from the matrix model side, which was at the end of the talk. So you start from any polynomial of large enough degree R, and together with a diagonal matrix, and then you consider such a measure on the Hermitian matrices. And the idea is you take your polynomial and you throw away the constant and linear Taylor coefficients when you expand about the diagonal matrix. So then it starts quadratic in M tilde, this shifted matrix, and then you naturally get, after expanding here this exponential properly, you get Riemann graphs with weights. And the weights side to the edges, you get from the quadratic piece, so the inverse, that's usual relation to covariance. And the higher valent vertices, they come from the Taylor expansion coefficients here of degree 3 to R. Good, so and Kontsevich model is a special case if when you take as potential 1/3 m cubed. You do all this and then you get the Kontsevich model. But here it's really, so there are very many polynomials as we know, so it's a very large family. Good, so what's the idea? So the method is, so the Elba and the authors introduced several families of generating functions for Kontsevich graphs, generalized Kontsevich graphs, maps, as you like, for those with ciliated maps, and also those with square. And then they proved, that's highly technical, various Tat, loop, Das-Schwinger equations, whatever you like. And main thing is also, this involves also, or can involve some auxiliary function H and P. So, and the main strategy is to notice that these auxiliary functions emit an extremely elegant solution. And then if you have this, the linear quadratic loop equations, which is really the heart of topological recursion, this comes for free. Just expand about infinity and it's already there. So yeah, one personal remark, if I'm allowed to say, this method is absolutely great. So I'm sure it works in many more examples, and as Alex Hock noticed, it even works in the example we are working on. So thanks a lot for this idea. And so, okay, well, to finish more or less, but it's covered in the talk. It's important to go to degenerate cases, so higher order TR. That's one aspect. And then all is about, well, this is now the part C of the picture, relation to intersection numbers. And here's more or less the setting. So there is a certain class, which is R-spin class, CW, And this is then integrated with appropriate number of Chern classes, psi-classes, take that number to get these objects. And the result is then that here these cumulants of certain diagonal matrix elements, so shifted around the diagonal of diagonal matrix. So so it's a diagonal matrix entry. So you take the correlations, the cumulants between them, and this matrix model can be expressed explicitly. So there are gamma functions and so on in terms of these intersection numbers. So that's the result. So integrability was known before. All right, I will not say much on it and only make a few remarks on the outlook in the talk. So there are relations to free probability, which is very exciting. So what I find extremely fascinating is the program to understand the large genus asymptotics and possible relations to resurgence. And also internally for the whole area, more about the XY symmetry of the spectral curve is very interesting. All right, so I think I should finish here. So